How do the pressure, volume, and temperature depend on each other for ideal gases and van der Waals gases? For ideal gas, PV equals RT. And we can just take the first derivative of pressure with respect to volume. And we need to specify the condition. The condition is we hold temperature constant. When temperature is constant, we can express pressure as a function of only one variable, that's V. And because temperature is constant, we can take nRT out of this first derivative. And then we take the first derivative of 1 over V with respect to V. I usually write this as V to the power of -1, and then we put -1 here in front, and then lower the power by 1, so it's going to be V to the power of -2. Therefore, the result is -1RT over V squared. And just a reminder, it's extremely important to write out the subscript T here to emphasize this is an isothermal process. Again, in physical chemistry, we deal with isothermal, isobaric, isovolumetric, adiabatic processes. If I replace this temperature here with a different variable P in subscript, that means P is being held constant. It's an isobaric process, and then delta P over delta V is simply 0. I can also replace this T with V, volume. I'm holding volume constant. Can pressure change? Yes, pressure may change with temperature. And then this delta P over delta V can be negative or positive infinity. So it's utterly important to write out this T in subscript to emphasize that we're dealing with an isothermal process. And this is when temperature is constant, how P depends on volume. And then how does volume depend on pressure? Similarly, we just have this derivation here. The result is -nRT over P squared. And these two, if you look at their subscripts, T and T, they're the same. So basically, it just tells you for a isothermal process, how does P depend on V, and then how does V depend on P. Therefore, these two are reciprocal to each other. And again, you have to check the subscript only if these two subscripts are exactly the same, and then you can say delta P over delta V and delta V over delta P are reciprocals of each other. And then the other derivations are easy. Delta T over delta V, V over T, T over P, P over T. They are really easy. I just want to emphasize that you have to specify the condition, whether it's isobaric or isochoric. For van der Waals gases, the equation is more complicated. This is so-called the attraction term. A stands for the attraction parameter, B is the repulsion parameter, and B is also the size of 1 mole van der Waals gas molecules. B can be determined by freezing 1 mole van der Waals gas into either liquid or solid, and then measure the molar volume of the liquid or solid. For example, if you have water vapor, the B value for water vapor, I guess, is roughly 20 milliliters per mole. Okay. So again, this whole term is the attraction correction. This term is the repulsion correction, and we can also express P as a function of T and V. Again, this A, when A increases, P decreases. It's because when the attraction between gas molecules increases, they collide with the surfaces, so less likely there's lower pressure. And when B increases, you can see this V minus MB decreases, and then therefore the pressure increases. Therefore, this B accounts for the repulsion between the gas particles, and also again B is roughly the molar volume of the same gas particle in the liquid or solid phase. Alright, and V minus MB is simply the available space for the gas particles. So how do we do delta P over delta V? Again, we have to hold temperature constant. If we hold the temperature constant, you can tell that there are two terms, both depend on volume. So we take the first derivative of this term, and nRT is a constant, so we have this constant here. And then we just take the first derivative of 1 over V minus MB. That's going to be just -1 here, and then V minus MB to the power of -2. And then using the chain rule, we need to take the first derivative of V minus MB with respect to V. That happens to be 1. Over here, it's easy to do. A times n squared is a constant. It's independent of volume, so we copy this an squared here. And then we have this 1 over V squared, which is V to the power of -2. We take the first derivative of V to the power of -2. That's -2 times V to the power of -3. And we have two negative signs, so they become a positive sign here. And this is V to the power of -3. And then we are going to use these one of the calculus rules. Delta V over delta P times delta P over delta V equals 1. If and only if they share the same subscripts. So we are holding the same temperature constant, and then dV over dP times dP over dV equals 1 for a isothermal process. Therefore, to get delta V over delta P, we simply just need to take the reciprocal of this, and it's here. And of course, you can further simplify this. And we can also express T as a function of P and V by transforming this equation. So we have this temperature as a function of P and V. And we'll do delta T over delta V first. T is the function of volume here when we hold a pressure constant. Again, over here, we're dealing with a isobaric process in which pressure is held constant. And this is the product of two functions of volume. So we'll have to use the product rule. So right now I'm gonna just take the first derivative of V minus MB, that's just 1, multiplied by this function, so over here. And then I'm gonna take the first derivative of this guy with respect to V. Again, we have this V to the power of -2, therefore the first derivative is -2 times V to the power of -3 times this an squared. Where does this pressure go? We're holding pressure constant here. And then the first derivative of this guy times V minus MB, we then simplify this whole thing. This is the simplified form. How about delta V over delta T? It's simply the reciprocal of delta T over delta V, as long as we have the same subscripts. Okay, we're looking at actually a isobaric process. In an isobaric process, V is a function of only one variable T. T is a function of only one variable V. You're looking at dV over dt here. For isobaric process, this is equivalent to dt over dV for isobaric process. So we're converting a multivariable calculus problem to a single variable calculus problem. So we just take the reciprocal of this, we get here, delta V over delta T. Finally, delta P over delta T is really easy. P is just a function of T. And this part does not depend on temperature when the volume is held constant. Very important here. I'm holding volume constant. And if I'm holding volume constant, therefore this part is constant. This part does not depend on temperature. Only this part. This part is a constant times T. It's nR over V minus MB times T. Therefore, delta P over delta T is just nR over V minus MB. Delta T over delta P is the reciprocal of this guy, as long as we have the same subscripts.